The interpretation problems of quantum mechanics are a popular subject on YouTube, as the screenshot shows. So when adding another movie, you have to do something special in order to stand out. The things done in this series are mentioned in the title. The first is to say that the problems are going to be solved, instead of just discussing them. And the other one is to list a lot of famous names. However, this list is not just clickbait, but these are the ones that are used to find the solutions, following this advice by Maxwell, to study the original sources. From the choice of the famous names, you can guess another aspect of the chosen approach. These are the ones that favor thinking in continuity and determinism, rather than discreteness and probabilities. Not that these concepts are done away with, but they are treated as the consequence of more continuous things, like Louis de Broglie did by trying to explain the discreteness of atomic spectra by the continuous processes of oscillation and interference. Another tool is the emphasis laid on practical things than those that can be measured, as for example advised by Planck. Here this is supplemented by trying to find illustrations for the concepts discussed as much as possible. And of course, there is always the general guideline of doing things as simple as possible. For this, the use of illustrations is also a great tool. So what are these problems with quantum mechanics? They turned up soon after its invention, and were serious enough to get all those that matter together in order to discuss them at the famous Solvay Congress of 1927. The main adversaries became Bohr and Einstein. He is seen talking at the home of Paul Ehrenfest in Leiden, the Netherlands, which was a permanent focal point of these discussions. The main topics were the role of continuity in physics and whether the formalism then under development was complete. Their discussions continue into the present day, nowadays mostly focused on the intrinsic properties of microscopic matter and the role of the human observer. The problems of quantum mechanics are highlighted by two famous experiments, the first one being the double-slit experiment, here shown in its archetypal form. One shoots electrons at a screen with two slits, and the intensity is measured by means of a photographic plate showing an interference pattern, like that of waves. What has become the standard explanation of this phenomenon is called the wave-particle duality, formally stated as: when the electron is on its way towards and away from the screen, it is a wave, while in the electron gun and in the photographic plate, it is a particle. This formulation comes almost literally out of a later discussion between Bohr and Einstein in a series of papers called "Can Quantum Mechanical Description of Physical Reality be Considered Complete?", also known as the APR papers, after the authors of the first part. Generally it was seen that Bohr had won this discussion, and his approach became known as the Copenhagen interpretation after Bohr's place of residence. And that became part of the way quantum mechanics is taught at universities. However, if you take the words literally and put them into physics, you get this picture. And this picture gives a highly uncomfortable feeling. What is a massive particle turns magically into a wave, and then into a massive particle again. This doesn't satisfy any standard of simplicity or physical intuition at all. And that is, of course, the real reason that this is still under discussion today. The second quantum problem stemming from these early discussions has become so popular that it has reached mainstream culture, the famous Schrödinger cat paradox. Here it is in more detail. Common sense says that the cat is alive or dead, depending on the radioactive decay. Quantum mechanics says that before a measurement, the state is in the superposition of all possible outcomes, so before a measurement, the cat is being both alive and dead. Only upon measurement, it goes into one or the other state. The formal name of what happens during a measurement is the collapse of the wave function. Shown is an attempt to make an illustration of it. And here is another one. Both illustrations, and these are the best ones that could be found, also signaling that nobody really knows what is going on here. This is what in more general terms is called the measurement problem. Here's what Einstein remarked about it and about the role of the human observer in it. Even an otherwise traditional physicist like Richard Feynman did not believe it, writing, "If a meteorite strikes a forest unseen by humans, there are always broken branches to be found later in order to check it has happened." The more principled objection to this Copenhagen view of measurement is that it is a form of anthropocentrism. It puts humans in the center, just as one did in the old days with the Earth, as in the illustration. And anthropocentrism has always been proven wrong. Conclusion so far, even with just these two things, there's more than enough reason to see problems with quantum mechanics. So on with it, and here we're gonna solve the two problems in 6 installments by turning back to those who built quantum mechanics in the first place and using common sense and imagination like they did. The first 3 parts after the introduction apply this to the ways de Broglie, Schrödinger and Dirac derived their seminal equations, which is not how they are presented usually. The first case to be taken up is that of de Broglie, who in fact came up not with one, but with 2 seminal equations. But if you do an internet search on the Broglie equation, you get only one of them, the famous wavelength relation, the one that in the 2-slit experiment is used to calculate the interference pattern. However, there are good arguments for taking that the other one, which is his frequency relation shown here, is the more important. And it is more fundamental in any case, because the wavelength relation follows from this one and not the other way around. In the title of the series, de Broglie is followed by Einstein, here in the center of the group together with Lorentz, whose transformations Einstein used. Einstein is included not because he is Einstein and attracts attention, but because he was the intermediary between de Broglie's idea and the top of the physics community at the time. And because de Broglie starts with Einstein's mass-energy relation of 1905. And Planck's quantization relation, but one has to draw the line somewhere. Over to the second source of basic quantum mechanical knowledge in the person of Erwin Schrödinger, who started with de Broglie's oscillation and wavelength relation and gave us not one, but 2 differential equations. He forgot to publish the first one because it couldn't readily reproduce the atomic states, and later it became known as the Klein-Gordon equation, but here it will be called the relativistic Schrödinger equation. The second Schrödinger equation became the famous one, with such nice illustrations, but here it will be treated as more or less a dead end, after it has been shown that, despite common usage, it is not a wave equation, but an amplitude equation. And because it is not relativistically invariant, which is a basic requirement for any fundamental treatment. So over to the third source of basic quantum mechanical knowledge, which is Paul Dirac. Dirac took the first Schrödinger equation, with its known deficiencies, and repaired these deficiencies. In order to do this, he had to increase the number of components of de Broglie's oscillation from 1 to 4, and what he got was a relativistic equation for quantum mechanical wave functions that indeed is valid under all circumstances, and came with the well-known prediction of antimatter. Here's an artistic impression of the equation in its relativistic shorthand form, which is not easy to decipher, but that goes for the equation itself too. This deciphering takes up part 4 of the series and involves the only slightly higher mathematics, something to do with matrices and symmetries, but in an understandable form. Contrary to the official Schrödinger equation, the Dirac equation will be used in the solution of the quantum problems, because it introduces a special kind of wave functions that also include spin. And because its solutions obey the exclusion principle, which is typical mathematicians' talk, because nature obeys nobody nor any principle, but nature does things, and that doing things leads people to formulate principles, etc. And therefore, and according to our rules formulated above, the exclusion principle is translated into something simple and practical as the exclusion of wave functions. The translation of the exclusion into something practical is one of the things to be used in the fifth part of the series that starts to build a model that solves the problems. The other steps towards it also follow the advice of Planck, taking as an example the pictures shown that were used to illustrate the discussions in the EPR papers. Here we will take this emphasis on the practical side of things a step further. This involves a rather natural-looking concept, but in this context apparently so unusual that it shocked the Nobel laureate. This is, used at the microscopic equipment used to measure the microscopic state, its cells also consist of microscopic particles. Here shown for the archetypal case, the double-slit experiment, in particular its screen. And, perhaps to be seen as a separate step, take one particle from the equipment to represent the entire equipment. So now we have a case of the interaction of two microscopic particles. It is in this context that the Broglie wavelength relation is derived, and everything else that is necessary for the kinematics of the situation, using the deterministic evolution of wave functions. And in the second part of the solutions, the reverse step is made, from microscopic back to macroscopic, the illustration showing the measured particle in interaction with all those in the equipment, here represented by the screen. And it is in this context that we meet the last in our list of famous names, David Bohm. But it is not the hidden variables or pilot waves for which he is known in quantum theory, but on the relation between the causal descriptions in the microscopic world and the probabilistic ones of the macroscopic, which he calls a one-to-many relation. This one-to-many relation directly applies to our intended path, with on the left the microscopic two-particle interaction to be developed with a deterministic evolution that obeys differential equations, and on the right its application to the situation of measurement, with a multitude of particles being involved, leading to probabilities and statistics. This separates the two conflicting descriptions and will solve both the two slits and the more general measurement problem. The next part in the series, on the Broglie, introduces the first steps towards the microscopic model on the left.